So what we are going to do as the first part of this course is that we will focus on the mathematics and the physics of turbulence. And then in the second part, we will start discussing about modeling and approaches for the model. So generally, we categorize flows, those flows that occurring in nature or flows in engineering applications into laminar and turbulent. Laminar flows are what we call predictable, meaning that the governing equations are the same. And as I told you in last session, governing equations, they do not care if the flow is laminar or turbulent or either compressible or incompressible. They govern all the states of the flow. If the flow is laminar, it's not actually it's not related to the equations, but if the flow is laminar, that's the state of the flow that we observe. Equation set is always Navier-Stokes, and basically it represents the whole range and all spectrum of the flow. Sometimes it is organized and we call it laminar, and sometimes it is disorganized. Uh, Here, predictable means we know the equations and we can solve them. So we can get results and predict what is going to be happened. We observe organized flow, nice and a smooth flow in terms of some observational characteristics. It's predictable, but this does not mean that the flow will be steady. It could be unsteady as well, or it could be transient and periodic. All these conditions can occur in laminar flow regime. And the most fundamental example to this is the vortex shedding from a cylinder. What happens if you have a two-dimensional cylinder and flow passes around this cylinder? We have alternating large vortices that shed from each side of the cylinder, and that vortex shedding forms what we call as von Karman vortex or Karman vortex street. You remember these. But that does not mean the flow is turbulent. Even inside these vortices, the flow is laminar. We we have laminates, not like planes, but they are spirals, and there is very little mixing in the flow. Between laminar and turbulent states of the flow, we have transitional state, which is um, in itself a complete standalone phenomena. You can spend one whole class, the whole semester on that. How the flow changes its geometrical and physical state from laminar to turbulent. That is understood, of course. The physics is known more or less. The transition mechanism happens differently in different engineering systems. In turbomachinery, for example, you could have all kinds of different transition mechanisms compared to the transition from laminar to turbulent happening in aircraft wing, for example. Those transition mechanisms and modeling them are really tough, and still there are big groups of people across the world who are trying to understand how transition occurs under different operational conditions in engineering systems, how transition occurs, and how we can model them mathematically. But in this course, we're not going to go into that. So when we start talking about turbulent flow, the same set of equations equally applied uh, for the turbulent flow, Navier-Stokes equations. However, when we observe the turbulent flow, it does not look like laminar flow. We observe some differences actually, and these differences are listed in here. Okay, so we said that the turbulence is unpredictable, and we mean by that it can produce, for example, 1,000 or 10,000 different solutions. So the question here is that uh, how we're going to handle this 1,000 different solutions, because you want to design engineering devices that will work with Floyd. You want to design aircraft as well as aircraft engine. You want to design wind turbine, a spacecraft that will re-enter the atmosphere at hypersonic Mach numbers. How are you going to design all of these if you cannot calculate the flow properties then? The nice thing is, yes, they are unpredictable, so you can predict what we call instantaneous flow field. But what you can predict is average flow field. These averages are obtained by solving appropriate equations, not the original Navier-Stokes equations, but with derived versions of Navier-Stokes, which we call them today as Reynolds average Navier-Stokes, RANS equations, which are statistically averaged equations, and we will see we will see those equations as well. So it's possible to calculate mean values. You may have no idea about instantaneous values, instantaneous flow, but you can really calculate in a certain degree of accuracy the statistically mean characteristics. So when we say unpredictable, we refer to the fact that we cannot predict the instantaneous on-look flow fields. For laminar, we can predict the instantaneous flow as well as the mean flow. So the second property is that it is diffusive. Whatever you put in a turbulent flow tends to get diffused very quickly. So that is related to mixing. Regarding this diffusiveness, I will write, uh, I will give some details about this diffusiveness. This diffusiveness, as I explained, causes rapid mixing in the flow. And when we talk about mixing, it's not just about mixing of two or more fluids, but also mixing of momentum. For example, if you have two flows of the same fluid coming and meeting each other, if their momentum level is different, there will be a very quick mixing of momentum. Similarly, if their energy level is different, there will be a very quick mixing of energy. This will increase grades of momentum or heat and concentration as well in the mass transfer. This is one of the most distinctive properties of turbulence. If you look at a flow field which looks random and rough, but does not exhibit spreading of velocity fluctuations through the surrounding fluid, if there is no mixing happening inside, the flow is not turbulent. So, for example, if you just leave some paint uh, inside the uh, let's say, do I have something that I can show you? Yes. If you just leave some paint uh, inside the tank, it will take weeks or months to get mixed. We want to know why turbulence makes mixing faster. Let's say some part of fluid uh, is A and some part of fluid is B, and if you put fluid B as a dye or as a red color inside the A, and then if you plot the concentration of B along this direction, let's call this direction y direction. You when you move along y, as I am showing in this left figure, you have these three figures, the left one, the leftmost one. When you move along y, there is, uh, let's say, first of all, when you're here and you move, there is no concentration of B, then you will reach the circle of B, and there is a full concentration of B, and then again, after you pass the border of the B, there is no concentration. So you will have a concentration, and this concentration, let's say it has some length called capital L. And if if there is turbulence in the domain, like uh, if you use a spoon and spin it, the shape of this bubble, this circular bubble, will start to get distorted significantly. And what we can observe is the same droplet looking completely different, like in the middle picture. So there is this droplet is completely different. For example, again, you have B and it is looking somehow distorted. If I repeat drawing the same plot again, I mean the plot of concentration of B along y direction, you will see that mm, it can go on and on, and another delta in another delta t time, it could look even more distorted, like what I have shown in the rightmost figure. Okay, but I fundamentally observe this. The effect of turbulence is to distort the general geometry and create finer and finer and finer scales. As you can see, the scale in here is L, capital L. Then it is getting reduced to a small l, and then after some time it is getting reduced to a smaller L prime, let's say sizes. These sizes, we call them as scales. Initially, the mixing was occurring around the surface of the sphere. That was my relevant scale. For example, the diameter of the sphere was capital L, but turbulence distorts the outer shell, and the mixing of the paint of the, let's say, red paint E inside, for example, water, which is A, has to happen on a much larger surface area. My relevant scales get smaller to the thickness of a small L. So if uh, my relevant length scale is not anymore capital L, and it becomes a small L, and it becomes a smaller L prime. Uh, the fundamental thing that is happening is still molecular mixing, but molecular mixing occurs in much smaller scales after, uh, let's say, turbulence, uh, and becomes very fast. Instead of uh, mix the whole bubble, you just need to mix these little small L's, and that can happen very quickly. Another example is, for example, drop of milk into a cup of coffee. Molecular mixing time scale, as I'm giving in here, is proportional to length squared divided by gamma, and gamma is the diffusion coefficient. This time is not proportional to L, but it is proportional to L squared. So if you have a lot of decrease in L, you will get a squared of that in how much decrease in time of molecular mixing. So this is the main reason behind it. So let's go back to this and let's see other properties of a turbulent flow. It's inherently means by itself, kendi kendine. kendi başına. Inherently three-dimensional. There is no such thing as two-dimensional turbulence. Although the mean flow, meaning that it is a statistically averaged flow. The mean flow can be two-dimensional. The out-of-plane component of velocity could be very small compared to in-plane components, but instantaneously anlık olarak all of three velocity components always, all the time, for all flows are more or less in the same order of magnitude. Why is this three-dimensionality important to us? Because we will see some modeling approaches and simulations approaches. Uh, they are separate, by the way, modeling and simulation. When we talk about simulation, in our objective is to solve instantaneous flow fields. Like larger simulation or direct numerical simulation are simulations. You can never talk about two-dimensional direct numerical simulation or two-dimensional larger simulation. When you observe a turbulent velocity field or pressure field, it looks rough or irregular. So I'm talking about irregularity of the turbulent flow field. It does not look smooth. There is a very sharp boundary between laminar and turbulent region. For example, if you are looking at a turbulent flame, you have a combustor and you are injecting fuel and you generate flame, which is a turbulent flame. If you look at the boundary or the geometry of the flame, it is not like very smooth and very uniform. It consists of many little flamelets and all kinds of geometrical variations. The geometry of turbulence is very rough. What generates that roughness is another story. We will talk about it later. The turbulence is actually a property of the flow, not fluid. And even it looks rough and irregular, it is still some phenomena that occurs under our assumption of continuum. So continuum approximation is valid also for turbulent flows. We are not talking about molecules. We are very larger than molecular mean free path. Still, the mean free path is very small. And generally, we observe that turbulence occurs at large Reynolds numbers. This is a problem for some engineering systems that should operate at very low Reynolds numbers. Micro and nano flows are such systems. In microscale pipes, viscous effects kill any vortex or any non-uniformity that can be generated in the flow, so you cannot have turbulence. In large scale engineering systems, in aerospace, around buildings, around cars, and so on, there is no doubt that there will be turbulence. And the last one is the dissipation. So the turbulent flow is dissipative. This means it dissipates energy. That is not good because in some engineering applications, you do spend a lot of effort, a lot of money to generate energy, and turbulence dissipates that energy, and that's not good. This dissipation may be indicated by total pressure loss in your engine compressor, for example. You designed it with pressure ratio of, for example, 30. After you test it and you see that you end up with 25, the pressure ratio. What's happened? You say, oh, it's because of losses. You lost the total pressure, which consists of static pressure and kinetic energy. When you start losing kinetic energy because of presence of turbulence, your total pressure gets reduced. So if the aim is to create minimum loss, we have to be able to control turbulence, or at least we have to know how turbulence gets generated and in what part of machines can we actually reduce those effects. Those are main properties or features of turbulent flows in general, and we will come back to few of these again later. So as I said, we are using sometimes some of these properties of turbulence are actually useful for us. For example, turbulence enhances mixing. So we just said that it creates interfacial area to enhance molecular mixing, and we just explained it in this figure. And one of the areas that we are using it is in combustor or combustion chamber of turbojet engines, for example. So we are trying to make the flow turbulent to increase the mixing rate. So some days also like in the mixer you want to create it, and some days you want to avoid it. Sometimes turbulence is good, for example, in external aerodynamics and some internal aerodynamics. Um, it prevents boundary layer separation. In gas turbine engine, turbulence increases heat transfer, so it is good for blade cooling. However, it is not good, for example, in applications of flow in pipes, because it adds more friction inside the pipe and flow resistance will increase. Or if you're trying to design a glider, it's not good. The turbulence is not good. You want to have a laminar flow everywhere, but sometimes you end up with the turbulence. Depending on your application, sometimes you may want it and sometimes uh, you may not want it. So there is a good example about golf ball preventing boundary layer separation. So it's not perfect sphere, you know. Why it's not perfect sphere? Because it has, it has some textures or depths over the surface. We call them dimple. Actually, 100 years ago, golf balls were perfect spheres. Normally, if a sphere is moving through a fluid flow, which is perfect sphere, so there is no disturbances on the surface. It is very smooth surface. Flow stagnates at, for example, this point. Okay, I think it was something like 80 degrees. I'm not. I think it's around 80 degrees. So then a laminar boundary layer is generated, and then it gets separated generally at about. You see, this is the laminar boundary layer, and it's separated around 80 degrees, more or less, in a very wide Reynolds number range. Now, if the flow separates here, is there any problem with my voice again? Okay,
No, no hocam.
okay.
Good.
So if it separates here when there is a laminar boundary layer, this means that uh, this region, the whole region at the back, is filled uh, with turbulent wake flow. And this height of this thickness of the wake is significantly big. And one of the methods to calculate drag force on an object like this is to compare the momentum loss with the wake within the wake to the initial momentum of the incoming fluid. I think some of you may remember this from fluid mechanics courses. If you do a volume control analysis, compare the exit momentum and inlet momentum, this momentum difference should be equal to the force in the axial direction, which we call it as a drag. So you generate a very big wake, as you can see, for example, in here, you see it's a very big wake, very thick wake that creates momentum loss. So there is huge drag on the perfect ball. When people realized this, they said, okay, how can we modify the boundary layer on the golf ball? If you can make it a turbulent boundary layer, it will not separate at this early 80 degrees. It will be resistant to flow separation because of turbulent flow, due to the better mixing of momentum of the fluid. So here again, mixing plays important role for us. When you put these dimples on the ball, they create little disturbances on the flow. So instead of separating at 80 degrees, now it is separating at some uh, more degrees, like 120 degrees from here. So as you can see in this figure. So what you have is a fluid flow more or less follows the geometry of the ball and gets separated somewhere in here. So the wake region gets much smaller, as you can see. This is a thin wake. This means that the drag on a dimpled golf ball is considerably less than the spherical golf ball. So when you hit this golf ball, it will go further because of lesser drag. This is just a simple example of using turbulent flow properties in real life, simple applications. We use this exactly the same approach in many engineering systems. If you require turbulent boundary layer and you want to obtain resistance to flow separation, you have to do something with your surface. If it is an airfoil, you have to make the airfoil a little rough, or you can put what we call turbulent boundary layer strips close to the leading edge to kick the boundary layer and make it transform to turbulent boundary layer as quick as possible. This is a very clever and smart way of making use of turbulence. Uh, okay, I have given this picture in here for you at the bottom. So I'm trying to make you get it used to what's the difference between modeling and what's the difference between simulation. So just keep these figures and typical shapes of the flow in a golf ball in your mind. So it's just try to remember it when we get into the Rans equations, Urans equations, and then get into the simulations like LES and DNS. So as you can see, there are different major big differences between simulations and modeling in turbulence. Okay. There is a variety of turbulent flows. So we generally categorize fundamental turbulent flows. The first one is the wake. And here you see a figure of a typical plane wake. So when velocity comes and hits this cylinder, it will make a plane wake for you. with some geometrical properties. This wake could be from a golf ball, airfoil, it could be from a wind turbine, it could be a wake of the whole aircraft or your car. There is a deficit of momentum behind the body. And at high enough Reynolds numbers, it is entirely turbulent. They consist of a very wide spectrum of scales, large to small eddies, and they are responsible for drag generation. So if you want to predict correctly how much drag your airfoil, for example, is generating, you have to predict two things very correctly: boundary layer development on your airfoil and wake development behind the airfoil. Another type is the jet. So the example is for a round jet is given in here. You supply some fluid and then using this nozzle, a round jet comes out from this. Or if you take a cross section of this round jet, you will come up with a plane jet that you're seeing in here. Um, these jets are kind of opposite of the wakes. If you plot the velocity profile, somehow it is zero and then goes to the maximum and then again goes to the zero. In the wakes, it is maximum and then goes to the minimum and then it is going to the maximum again. This is the second fundamental example of turbulent flow, the jet. The point is modeling the wake and jet flow using the same turbulent model may not perform similarly in these two cases because the physical process are different. So interestingly, it is true that you cannot use the same models to model jet and wakes the same way. The third typical type is the mixing layer. For example, you have um, two flows. One is from upper side and one is from uh, lower side, and they are separated by some flat plate. And another flow, this flow is coming from the lower side, and they meet uh, they meet at some point on the flat plate and they start mixing with each other, and this mixing process creates a shear layer. Okay, what you see in here is a shear layer, and the velocity profile looks like this, so like a shear. They also require other approaches rather than the approaches using for the wakes or for the jets. Another one is the plume jet. So the plume jet, as you see it in here, it's a jet in cross flow. So there is a jet coming from the lower side of this plate, let's say, and the flow is normally coming from left to right, and the jet is coming from low bottom to top. So this generates another typical turbulent flow that we call it as a plume jet flow. There is and actually this creates the very completely turbulent and complex turbulent region with all of these horseshoe vortices and some shear layer in the jet. There is a center line jet, there is induced vertical velocity, and it is very complex, and the calculation is very complicated. And also you have the boundary layers. the last we call turbulent flow is a boundary layer. And the boundary layer is very general topic. It could be a boundary layer of a wing to a boundary layer of Earth, which we call atmospheric boundary layer. So boundary layers have their own properties. In order to have a boundary layer, you have to have a flow over a solid surface. And if the solid surface is stationary, the fluid particles near the surface also they have to be stationary. We know it as no slip condition, and you may have heard of it before in your fluid mechanics courses. So near the surface, velocity is zero, and this velocity profile, the profile, this velocity profile solution is unique, and its model requires a unique effort, and it's completely different than the other flows that we just mentioned to you, the wakes, jets, mixing layers, plumes, because you do not have zero velocity except for the jet, which we are not interested to model the exterior part of the jet. So as you can see in here, there is no zero velocity. In here also, for the jet, the outer plane is the outer part of the jet is zero, but we are not interested. In here, there is no zero velocity, but in here you have zero velocity. So uh, that shape of velocity profile, the zero velocity affects the whole distribution substantially.